Hello, I'm Dr. Christy Patton-Lukes, and in this lesson we're going to be looking at vapor-liquid equilibrium and introduce ways that we can solve multi-component problems with some simple equations. So multi-component equilibrium compositions are much more difficult to predict than the simple binary cases, especially with one liquid that can condense out. The best thing to do is to use actual data. For instance, Perry's handbook has much of the data that you would want for very common systems. The methods that we're going to be looking at will give us some rough estimates, which are useful in that they will allow us to verify that the more complicated methods you'll be learning about in future courses make sense. Now, one thing that I want to remind you as we move forward using Gibbs phase rule, if I have no reactions and I have two phases, then the degrees of freedom will be equal to the number of components in this case. And so that's the number of variables that will need to be specified in order for the problem to be solvable. Now we're going to have two very simple rules that we're going to use for two-phase systems. Neither of these is perfect, but both of them are a nice simplification in certain cases. So the first of these is Raoult's law, and we've been using this. This is the multi-component version of it. It's still looking for things to be an ideal mixture, which means that the molecules behave nicely when they are put together. And it says that the partial pressure of each component, or any particular component, is equal to the liquid phase composition times the vapor pressure of that component at the particular temperature of the system. Now this is going to be pretty good when the system is pure A. Of course, if it's A in a multi-component mixture, and there's very little of anything else, then those other things will not be well described by Raoult's law. We frequently will use this, however, for systems that are just, like a third of each of three components. And we'll use it a lot of times when it's not even a very good approximation. But it will be best when the liquid is essentially pure A. Now, Henry's law is going to be for that case where you have virtually no A. So in that case, it looks very similar. You have the partial pressure, which is the mole phase component fraction times the total pressure, and that's going to be equal to the liquid phase mass fraction, or mole fraction actually, times this HA of T. So instead of the vapor pressure, we're going to replace it with HA of T. This is a Henry's law constant. It's a value that works, okay? Now, these numbers that will go in here are going to vary with temperature, and for many systems, we can find that data in Perry's handbook. If you have not yet located Perry's handbook, if you are an AICHE member, this is one of those things that is available through the library of AICHE. Otherwise, you'll need to find it in a reference library somewhere. Now, this is going to be best for the case when you have virtually no A present. So if you have something, let's take a can of soda pop. Right, okay, so there's my can of soda pop. There's the little ring tab on it. Okay, inside there I have essentially H2O and some CO2 gas that's formed at the top and a few little CO2 bubbles that are dissolved in there. For the liquid phase, it's mostly water with very little CO2. So the H2O will be well described using Raoult's law, and the CO2 will be well described using Henry's law. When in doubt, most of the time we default to Raoult's law and we just acknowledge that it's not going to be all that perfect. So let's look at an example using Henry's law. This is for the case of air dissolved in water. So this is an important concept for my pet fish. Okay, he wants to make sure there's a little bit of air dissolved in his water. The Henry's law constants can be found in Perry's handbook, and there are a few of them within the text of your textbook here. But if we assume that the air contains 3.5 mole percent H2O at 1 atmosphere, how would we know that? Using the definitions of humidity, getting a weather forecast. We know that the pressure is 1 atmosphere. How much air is in the water? So we've got a little bit of water in the air. I want to know how much air is in the water. So the first thing I need to do is gather data for Henry's law. In Perry's handbook, you'll find that it says that H times 10 to the minus 4th is 7.71 atmospheres. So to solve for H, it means that H is 7.71 times 10 to the positive 4th atmospheres. Now, there's always a big question about whether or not I'm supposed to be using Henry's law or Raoult's law. And in this particular case, I have air and I have water. Now, the air is very dilute in the liquid, okay? The water is very concentrated in the liquid. The vapor is just the opposite. But to make the decision, we look at the liquid phase. And so, based on this, air is going to be analyzed using Henry's law, and water would be analyzed using Raoult's law. Okay? So, I can use Henry's law and this constant here for air. I cannot use it for water. So for air, Henry's law says Y for the air times the total pressure, this is my partial pressure of air, is equal to X for the air times the Henry's law constant for the air. Now I have the Henry's law constant. That's what we just looked up. I have the total pressure. It's given as 1 atmosphere. I am looking for how much air is in the water, so in the liquid. So I'm looking for XA. I have P and H. I also almost have Y for the air. It says the air contains 3.5 mole percent H2O. Therefore, the balance should be air. So 1 minus 0.035 means Y for the air is 0.965. So substitute these numbers in to solve for X for the air. I find 0.965 times 1 atmosphere over 7.71 times 10 to the 4th atmospheres. Make sure your units cancel. They have to cancel. And I end up with mole fraction for air in the liquid is 1.25 times 10 to the minus 5th. Now this is a good opportunity to practice using parts per million. So to convert to parts per million, you multiply by 1 million. And so therefore this system has 12.5 parts per million air in the water. Now, frequently we're going to talk about things, and we'll do a lot more of this in future courses. But we're wanting to introduce the concept to you now. We'll talk about something called a distribution coefficient. This is just simply a way of relating the XA and the YA for a system. And if you look at Y divided by X, so the vapor phase divided by the liquid phase, that's going to be K, this distribution coefficient. We're going to find some equations for these in some future courses. For this course, we're going to sort of treat them like they just come from magic, okay? But one of the things that you can do that's pretty easy is something called a de Priester chart. Now, de Priester charts were created back when there were no computers, and so there weren't even calculators. So people were doing things using a slide rule, and the calculations are very complex. So therefore, someone graphed these for basic hydrocarbons. So for some of the light hydrocarbons, methylene, ethylene, ethane, propane, anyway, a lot of these guys here. These wiggly curves are the information for a particular substance. And pressure and temperature are on either side. And so the way you would use this is you find your pressure, okay, I'll assume this is my pressure, and you find your temperature, and I'll use temperature of 30 degrees Fahrenheit. And what you do is you draw a straight line connecting those 2 points. And for each substance, where it crosses the curve would be the K value. Okay, so this curve you read K values, and that tells you for ethylene, you know, just what the number is there. And it's about 6 something, okay? I'm not expecting you to be an expert on this. I just want to introduce you to the concept. If you really want to know what's going on with a vapor-liquid mixture, and we will need to do that, much of what chemical engineering is about, so solving evaporation problems, condensation problems, or really important for chemical engineers, distillation problems, we're going to need to know a lot about these vapor-liquid equilibrium problems. And we're going to be doing a lot of solving bubble point and dew point problems. Now, what I've shown here is one very well-behaved system, benzene plus toluene. And in this particular case, I have a graph of temperature versus X and Y and pressure versus X and Y. Now, in this particular case, we're going to read temperature or pressure along the vertical axis, and the horizontal axis is going to be mole fraction, and it's of both the liquid and the vapor. So X is my liquid, and Y is my vapor. But we can put both on the same scale, and we know that they have to go between 0 and 1, so the curve is limited between 0 and 1. And what one finds is that I have liquid, okay, with the first bubble of vapor forming at a lower temperature than where I have vapor with that first drop of liquid, okay? So in between, I have liquid, well, let me change colors. Liquid plus vapor, both in between. Down here I have, this is going to be like a compressed liquid. Up here is like a superheated vapor. And this makes sense that higher temperatures would be more vapor, lower temperatures would be more liquid-like. And for pressure, I'm going to have a similar looking diagram, but there's a really important difference because as I apply more pressure, so I increase the pressure, this is going to cause the molecules to come closer together, so my compressed liquids are above, and my superheated vapor is below. And in between is going to be that liquid and vapor mixture. And if I fix a particular, let's say, pressure, or it could be temperature, and I look across here, the liquid and vapor that are in equilibrium with each other are separated a certain distance. This is the liquid phase composition, and this is the vapor phase composition. And so this is a useful way of presenting data for binary mixtures. Now, frequently we'll be wanting to do some bubble and dew point calculations, predict the temperature or the pressure where that drop of dew first forms, predict the temperature or pressure where that first bubble forms inside the liquid. The way we usually do these is if we can just, for today, for this course, assume that we have an ideal solution, okay? Now, in an ideal solution, I'm going to assume that the vapor is an ideal gas. I'm going to assume that the liquid is going to obey Raoult's law for all the compositions, okay? If I will make those two really big deal super simplifications, then I can create some formulas. And the idea here, well, both of these equations would be valid any time, but for if you are wanting to know when the bubble point, okay, so bubble point is when I have a whole lot of liquid and I have that first little bubble being formed, okay, then the easiest thing to do, the easiest form of calculation is if I know what pressure this is at, I want to solve for the boiling point temperature. If I know the liquid phase compositions, then Raoult's law says that the partial pressure is equal to the liquid phase mole composition times the vapor pressure. Okay? But the sum of the partial pressures is the total pressure. So therefore, we can come up with this equation. Okay, just doing this for all the various components in the mixture. And if I happen to know all the x's and I know pressure, then no big deal. If I happen to know x and temperature, okay, if I know x and TBP, this is super easy, right? I would solve for total pressure, and then I could use that to solve for the vapor mole fractions. Okay, so various combinations of data that I might have. Some are going to be much easier to solve than others. Now, dew point calculation is the one where I have a gas and I'm waiting for that first drop of liquid to form. Okay? In that case, usually what you end up knowing is pressure and the mole compositions, right? You have a gas, so you know that composition. Before we had a liquid, we would know that composition. And so in that case, using the same basic formulas, right? There's my same basic formula, okay? Except what I'm going to do is I'm going to rearrange this to solve for x. So x is going to be yi times the total pressure, okay, or the partial pressure if you'd rather, divided by the vapor pressure of the substance. And then I couple that with the fact that sum of x's have to be 1. And so if I add all those up, I can solve for the temperature. Now in our next little video lesson, I'm going to solve one of these. I'm going to solve a bubble point problem. You could use the same technique with this equation to solve a dew point problem. There are many other variations on the problems. For the most part, we're going to save that for a thermodynamics course. But also, if you read in the textbook and study their examples, they're going to show you several others. So this concludes this portion of the lesson. The next little video is going to show you how to solve one of these problems.